First question, I'm gonna write it on the board. It's not very long. And this is a heat up solution. So dissolving 15.15 grams of potassium nitrate. You know what is distilled water, Mr. Harding?
No.
Some of the distilled water like when you strain something.
No,
Distilled water.
not strain.
Like purified water.
Yes, but it's not strain. The wrong choice of word. What is this name of this compound, Mr. Harding? What? Potassium nitrate. Because remember that in the exam, they're mainly gonna write the component word, and you have to know to write the formula. So you have to start get practice to know to write formula from the heat change equal to the mass the mass. So remember that we're going to assume that the mass of the density of distilled water is pure water. So actually distillation is a separation technique, but I skipped it. I'm going to do it like next month. Alright, I'm going to do separation technique. I have both fractional distillation and simple distillation. So distillation is really a separation technique in which we use to purify water. So actually, you're going to boil the water and then it's going to go to a condenser and it will condense back to liquid. But we will have the thermometer and measure the boiling point for water is 100 degrees Celsius. So we have water boiling at 100 degrees Celsius, only the water vapor will come up and condense. Right? So the mass, the total mass is going to be 100 for the water plus 15.15 for the potassium nitrate. This is going to be 100 plus 15.15 for the mass times the specific heat capacity for water is 4.2 joules per gram per degree Celsius times the change in temperature is 10.2 degrees Celsius. Sometimes when they are giving these questions, they can give you the initial and the final temperature. So you have to look out for the questions in that format. In that case, you'd have to subtract the initial minus the final, or the final minus the initial to get the temperature change, right? But in this case, the temperature decrease, meaning it's not an exothermic or endothermic reaction. Endothermic. So this process was an endothermic process because the temperature decreased. So it would be positive overall. What do we get for the answer here? So this is 115.15 times 4.2 times 10.2 equals
700.
4933. The value that we get here, 4933, is the energy released from 15.15 grams of KNO3. Right? Therefore, the mole 01, which is, we're saying here this is 1 mole. Following? What's the answer there? Getting some 32,887.
32,887.
Joules per mole. Can remember that if we check the value that we got from the calculation was for 15.15 grams. But we know that the mass of 1 mole of potassium nitrate is 101 grams. So the equivalent for this would be 32,887 joules per mole. And if we convert from joules to kilojoules, we'll divide by 1,000. And sometimes they will ask for the unit in kilojoules per mole. So you have to know that conversion as well. So kilojoules common K, capital J per mole. Because a capital K is kelvins when we talk about SI unit. So kilo, common K. Right? Great question. Right? Alright, so 50 is the next question, is a heat of neutralization question to calculate, right? 50 cm cube of sodium hydroxide solution with a temperature of 29.4 degrees Celsius and a concentration of 2 moles per dm cube is added to 50 cm cube of sulfuric acid with concentration 1 moles per dm cube and temperature 30 degrees Celsius. The maximum temperature of the solution after mixing is 43.2 degrees Celsius. Determine the heat of neutralization. That's the question. No, so as I said before, whenever you get a heat of solution, heat of reaction, heat of neutralization, you have to form, right? So first heat change equal to mass of a solution here, a reaction. What's going to be the mass here? 50 plus 50. How do we get this 50 plus 50?
The 50 cm cube of sodium hydroxide.
2 moles.
We're adding the 50 cm cube of sulfuric acid.
And we assume that the density of these dilute solution is the same as water, as pure water, which is 1 gram per cm cube. So if we have 100 cm cube of this dilute solution, we're assuming that is just equal to 100 grams. So we have 100 cm cube in total, just equal to 100 grams. So this is why we can do this 50 plus 50 cm cube, put it in grams. Make note of it, you know. This is the part of that I wrote down those 3 assumptions step by step for you. They assume that the density of dilute solution is equal to the density of pure water, which is equal to 1 grams per cm cube. And the specific heat capacity for the dilute solution, we're going to make another assumption that is the same as that of pure water. This is going to be 4.2 gram joules per gram per degree Celsius. And the temperature change would be 43.2 minus 30 plus 29. So I have to take an average. Temperature. Which is 100 times 4.2 times, that is approximately what? 13 point something? Look what the book says, what's the answer for that? The book got 13.5 here. For the average. When the average distance subtracted 13.5. You got something similar? What do we get here for the answer? Heat change. Following Miss Williams, step by step here. We'll get for the answer here.
670
670.
joules.
So remember that This would be the heat
I know
change
that.
when that specific number of moles of the substance react. But remember that the definition is when 1 mole of water is being produced. So let's write the equation. I want to put some figures right here. So for the NaOH was 50 cm cube, concentration was 2 molar. 50 cm cube and 1 molar. Balance is we have a 2 here. Two sodium. So 2 hydrogen plus 2 hydrogen, 4. 2. Alright. Now, if we calculate the number of moles of sodium hydroxide, this is 50, this is 2 molar cm cube. So 2 cm cube. X mole is in 50 cm. It's 50 times 2, 1000. What's the answer here?
10. 0 pound. 0 pound.
Oh, do the calculation. Alright.
0 pound.
0.1?
What?
No. Correct?
Yeah, no.
No, so if the mole ratio sodium hydroxide to the water is 1 to 1. It simply means that 0.1 moles of this will produce 0.1 moles of water. Following? So we could have used any one of the reactants. However, in this case, most likely they use a 1 to 1 mole ratio. But nonetheless, just to confirm it, we should double check over here. So this is 50. This was a 1. This is 1 mole, 1000 cm cube, X moles in 50. 50 times 1 divided by 1000. What do we get over here?
0.05.
0.05?
Yeah.
No. So even if we should take it over here, the mole ratio from this is 1 to 2. So it's still end up forming 0.1 moles of water over there. Following my Carlin? So whichever reactant you had chosen would still end up with the 0.1 moles of water being produced. So this heat change here is equivalent to 0.1 mole of water. So we have to find out how much is 1 mole of water would produce. So from this, therefore, we can see mole concept will really overlap with these stuff. Therefore, 0.1 mole H2O produce minus 5670 joules. Therefore, 1 mole produce X joules. What's the answer here? So 5670.
670.
What?
5,600.
Alright, 56.
One negative.
No, what's the negative? It's gonna be negative. Overall, it will just be negative.
0.1.
See what is actually the answer.
0.1. Oh,
56.7.
56. Subtract 1. Decimal place.
So this was in our 56. Let's give it in joules first. Alright, confusion. 56700 joules per mole. That's what you will get first, right?
That's the answer.
Equal to R, we put it in kilojoules.